Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We are going through a series of lectures related to the third semester and the paper 3 with the title Physics of Materials. This is lecture number 2. The title of these lectures come under bondings in solids. Now, the contents of today's lecture are types of bondings, octet rule, ionic bonding, and a calculation of lattice energy. When we talk of atomic bonds in solids, the bonding represents the balance between the two forces, namely the attractive and repulsive parts involving electron and the positively charged ions, because in ionic solid, the main name ionic solid means the collection of positive and negative ions, or whatever be the thing, even in metallic bonding, the Coulombic thing, attraction will be there and then repulsion will be there. So, E n, the net resultant thing, will be the sum of the two energies. The attractive part, the E A refers to the attractive energy and E R refers to repulsive energy. In general, in a case of ionic solids, if you go deep, you will find that the net energy will be given by, or the total energy of the ionic solid will be given by the two terms. The attractive part will be minus A square by R plus B by R to the power of n, and this A is called the Madelung constant, and E is the charge residing on the positive ion or the negative ion, or is the distance which separates the positive and negative ions, and B is some other constant, and n is some unusual number, right. We have R square with regard to force, with regard to potential, you got R for the attractive part, that is coming from the Coulomb's law, but whereas this repulsive part comes from quantum mechanics, from the through the Pauli principle. So, this R n is this n, the so called repulsive exponent, will assume unusual values, right. They are not R square or whatever be the thing, right. It is unusual thing, because it comes from quantum mechanics. When the net force between the attraction and repulsion is 0, there will be stability, right. In terms of energy, we have a stable bond when the potential energy of the system is a minimum, right. This is what you see here, the potential energy, the attraction, as I told you, below 0, negative sign attraction, The positive sign refers to repulsion, the negative is attraction, and this distance is the interatomic separation, or right. This is the repulsive energy. This attractive energy is a long term, the Coulombic force is a long range force, right, the long range force. So, it exists even at large interatomic separation. You have got one atom here, another atom here, and the long range force, the attractive part. The repulsive part is short range, and the resultant of these two, the attractive energy and the repulsion. You look at this point, you have the the positive repulsive part, and then the attractive part will be here, right. The resultant of these two, right, will be this much from here to here, and this net energy corresponding to this distance is the so called the cohesive energy, right. Let me, I will go back to this is called the cohesive energy. This is the attractive part, this is the repulsive part, and this is called the cohesive energy or the binding energy, as I showed in the last lecture. Okay. And so, the one should understand what we mean by cohesive energy, and the derivative, this you have the net energy E n, and the derivative of d E n by d r is equal to 0. E n is the net energy. For r is equal to r naught, which is the equilibrium bond length, E n will be equal to E naught, and E naught is called the bond energy. Let me go back, this is called the binding energy or the cohesive energy. In the case of hydrogen atom, what is the energy that should be supplied to dislodge the electron, to remove the electron from the hydrogen atom? It is 13.6 electron volt. That 13.6 electron volt in the case of hydrogen atom will be this much. Similarly, in any solid, if you take an ionic solid, how much energy will be supplied to break the ionic bonding, that is the bonding that exists between the positive ion and the negative ion. How much energy is required to break the bond is given by this much, or this is the binding energy, right. Negative sign refers to the binding energy. If you supply this energy, it is the energy required to break the bond. It is called the cohesive energy. The understanding of cohesive energy is important, right. So, the types of bonding. Now, I told you some time back different solids have I mentioned about copper and silicon and so on. So, these bondings which are existing in silver, copper and NaCl, they are called the primary bondings, because the bonding energy will be very large. The primary bondings are of three types, namely ionic, metallic and covalent. I told you again, the valence electrons are mainly responsible for bonding in all the three cases, right. And there is a secondary force which are clubbed together by you have the van der Waals bonding, it is fully quantum mechanical origin. Then the hydrogen bonding, they come under so called the secondary forces, right. Okay. They are all can be explained only on the basis of quantum mechanics. The cohesive energy is nothing but the energy required to break the solid into the constituent atoms. Solids are made up of free atoms, and for instance, you take NaCl, free Na and Cl atoms combine together to form NaCl solid. You bring free atoms Na and Cl and combine them, but when the combination takes place, you do not have free atoms really in a NaCl solid. It is ionic solid, it consists of Na ion and Cl ion. We will understand as time proceeds how atoms are made to become ions, what makes the atoms to go to positive and negative ions. Again, go back to cohesive energy. The cohesive energy is the energy of the crystal, that is the difference between the energy of the free atoms crystal energy minus the crystal energy, right. The difference in the crystal energy and the energy of the free atoms. The crystal is like this, right. The free atoms are separated by infinite distance. the energy required to bring the atoms at infinite distance from infinite large from separated by large distance to form a solid, the energy difference between these two, the free atoms and the crystal, the difference between these two is called the cohesive energy or the bonding energy. Cohesive energy refers to, or it means what? Cohesive energy refers to the energy required to break the solid into its constituent atoms. Now, this again this is called the cohesive energy, right. This is the, I think I need not repeat once again, this is called the cohesive energy. And what is this distance? If you have got a positive ion here and a negative ion somewhere here, when you bring the negative ion here towards the positive ion, now this is the distance at which the energy will be minimum, right. The energy, the total binding energy will be minimum for when you have got one ion here and another ion here. This is the distance which separates these two ions, and this is called the equilibrium interionic separation or interatomic separation, right. That can be measured by X-ray diffraction and so on. R naught is the equilibrium, the interatomic separation, this is called the R naught, the equilibrium interatomic separation or interionic separation, and this distance is not a theoretically calculated distance only. It can be experimentally measured by very many techniques, and like neutron diffraction or X-ray diffraction. X-ray diffraction is the conventional one that is used. This can be measured by X-rays. U naught is the binding energy, that is the U naught is the binding energy or the cohesive energy. And I think therefore, note that the repulsive part comes from the Pauli principle. In the diagram which I showed earlier, there is a repulsive part apart from the attractive part. And now, this shows the periodic table. Why I am showing the periodic table is I will come back to it again. We have elements here, you have atoms like hydrogen, lithium, sodium, they belong to the first group. There is a second group. I mean, what is the first group? It can give an electron easily to some other atom, right. So, they are called the electropositive elements. So, electropositive elements are atoms which can easily give out electrons, whereas electronegative is the one which will readily accept the electron, right. Fluorine is the superhalogen, I will come to it later again. Now, look at the simplest atom, namely the hydrogen atom. You got a proton here, right, the center, right, you got a proton here and you got an electron. So, you got only one electron in the hydrogen atom. So, it will be in the first shell. It can be excited to the other shells n equal 2 and 3 and so on, but the total number of electrons is 1. There is nothing like valence electron and so on. But let us go to the case of lithium. Now, lithium has got atomic number 3 and the electronic configuration is 1s2 2s1. You see the 3 electrons here, right. The 1s2, the 2 electrons are found in the first shell or the first orbit. The third electron is in the second shell, right. So, you got 1s2. Now, the 1s2 has been put in a bracket, that means they are the core electrons, right, the core electrons, whereas 2s1 is the valence electron, right. It is a valence electron. What is the valency of lithium? It is 1. Valency of lithium is 1. Let us go to sodium, right. Let us go to sodium atom, the atomic structure or electronic structure of sodium atom. What is the atomic number of sodium? Atomic number of sodium is 11, right. There will be 11 protons to balance the 11 positive protons, positively charged protons. There will be equal number of electrons, that will be 11 electrons. The electronic configuration 11 comes from the atomic number 11. So, it is 1s2, 2s2, 2p6, then 3s1. These are all things which one studies in the high school. And again, the electrons that you find in within the square bracket, they call the core electrons, and this is the valence electron. So, valency of sodium is again 1. Now, why I am showing all these pictures of lithium, sodium, potassium and so on, is make you to know the difference between core electrons and valence electrons. From what I have told so far, you would understood what I mean by core electrons and valence electrons. At this point of time, we will have a break and we will resume the rest after the break. Welcome back after the break. Let us look at the electronic configuration of inert gases. What are the inert gases which you have? There are helium, neon, argon, krypton, xenon and radon. Where do you find the periodic table? You find the last group, the first group or the monovalent lithium, sodium, potassium, etc. The last group contains these atoms, right, that is helium and so on. Now, the atomic numbers are given here 2, 10, 18, 36, 54 and 86. Their electronic configurations are given here 1s2. Now, you find here for neon you got 1s2, 2s2, 2p6. Argon, the electronic configuration will be 1s2, 2s2, 2p6, then 3s2, 3p6. Then you have for other atoms, right, krypton, xenon and radon. Let me ask you this question from the table that you see here or I show here at this point. What do you find? You find that the S2p6 is found after the bracket. What about the electrons inside the bracket? They are the core electrons, right. The electrons which you find outside the bracket are called the valence electrons or they are the valence electrons. The important point to be remembered always is it is the valence electrons which play a very important role in deciding all the properties, almost all the properties of all materials. Now, in these what is the commonality? That is they all have, excepting helium, all atoms, the inert gas atoms have got a S2p6 configured at the end, right. S2p6 means S2, there are 2 and 6, right. 2 plus 6 will make 8. So, you will have 8 electrons in the outermost shell. So, if you have got 8 electrons in the outermost shell, what do you know about inert gas atoms? Why are called inert gas? Why is called inert gas? Because they do not react or interact with atoms, right. It is difficult to break these atoms. They are inert, they do not accept the electrons, they do not donate the electrons, because the fact that they already have filled shells, right. The S state can have only 2, P can have only 6, already the electron, the electronic structure is closed, so they cannot accept electrons, they do not want to give the electrons also, they are inert, right. Because they are inert, they are highly stable, right. So, they are highly, when do you get stability? When the number of electrons in the outermost shell is 8, right, you get greater stability. So, in order that the atoms acquire greater stability, they should obey what is called the octet rule. What do you mean by octet rule? Having 8 electrons in the outermost shell is the best thing. Why? Because then only the atom will be highly stable, right. For better stability, the atom should have 8 electrons in the outermost shell. So, I asked the question, how many electrons do you find in the outermost closed shell that you see from this table, right. So, you come across what is called octet rule. Atoms with 8 electrons are very stable. Electronic arrangements get adjusted to obtain the octet arrangement either by transfer of electrons or by sharing. In all bondings, electrons have to adjust themselves in order that the atoms go to attain the octet structure, right. The octet rule is important, right. The octet rule should be borne in mind, should be kept in mind when you are talking about all the 3 primary bondings, right. In the secondary bonding, that is not very important, but in all the primary bondings, they are very important, right. So, okay, then the inert gas structures, the octet rule. Why are these gases called inert? As I told you, atoms with 8 electrons in the outermost shells are more stable. So, every atom will have a tendency to attain the octet structure, in order that it becomes very stable, right. So, when we pass on to ionic bonding, covalent bonding, you will understand these things better. Now, we will pass on to the ionic bonding. Count the number of electrons. What happens to sodium and chlorine atoms, right? The electron numbers are to be counted in Na and Cl. Na will have neutral sodium atom will have 11 electrons, neutral chlorine will have 17 electrons. They ultimately become ions. Na becomes a positive ion and chlorine becomes a negative ion. How will they become ions? That of course, you should know, right. So, in order to attain the octet structure, what kind of forces will operate between the ions? Between two ions, one is positive charge, the other is negative charge. Obviously, the Coulomb's law will come into operate, right, will come into operation. Okay. So, ionic bonding occurs between positive and negative ions. It requires electron transfer, right. Now, you have a stable sodium atom having 11 protons and 11 electrons, chlorine will have 17 protons and 17 electrons. Now, what happens is this an electron will be jumping from here to here. Why should it jump? Instead of having 11 electrons, it will be better to have 10 electrons. So, that it goes to neon structure 2 plus 8, right. The outermost will have 8 electrons, right. By acquiring 1 electron, what happens to chlorine? Chlorine again goes to S2p6 configuration. Outermost shell will have orgone structure, right. The stability becomes better. So, therefore, by losing 1 electron, it will have 2 plus 8. Here, by gaining 1 electron, chlorine becomes, as the number of electrons will be 2 plus 8 plus 8, 18 electrons. You will have 18 electrons and this will have 10 electrons. Thereby, both of them attain the octet structure, leading to greater stability. That is the reason why this becomes a, this is ready to give out an electron, this is ready to take an electron. Therefore, what happens now? This becomes a positive ion because the electron is lost, because this is acquired electron, this becomes a negative ion. Between the positive ion and negative ion, there will be certainly the Coulombic force which will come into operation. So, the Coulombic attraction is the one that is primarily responsible for attraction between the ions in the ionic solids. Okay. Then the larger the difference between the electronegativity, better will be the ionic bonding. One should know what is meant by electronegativity. The difference in electronegativity should be large. Now, example is Na and Cl. Where do you find electronegativity? I showed you a table wherein I showed that there are electropositive elements which are willing to readily release the electrons, right. Whereas, on the right hand side you have got elements which are highly electronegative, which are ready to receive the electrons. These atoms release the electrons which are on the left hand side, they are ready to release the electrons, they are called electropositive. The atoms which are on the right hand side of the periodic table, they are ready to receive the electrons. So, they are more electronegative, whereas these are called electropositive, right. There are electropositive atoms, lithium, sodium and so on, beryllium, they are electropositive. If when will you have larger electronegativity difference? It is if you combine the first group and the 7th group here, that is the group prior to the inert gases like fluorine, chlorine, bromine, iodine, astatine. Now, they are highly electronegative, which is called the superhalogen. Fluorine is called a superhalogen. in the Pauling scale, superhalogen chlorine, fluorine will have the highest electronegativity or the ability to attract the electron, whereas cesium, which is found diametrically opposite in the first group, that has the electropositive value, the least electropositive value. You have got cesium point, you have got a small electronegativity which is given here 0.7 as against 4.0 here fluorine. So, it is easier to form cesium fluoride, right. Cesium will give out an electron, fluorine will accept the electron. Similarly, you can have Na here will give the electron to chlorine. So, chlorine will accept the electron, whereas sodium will release the electron, thereby NaCl will be formed. So, for the formation of ionic solids, the electronegativity difference should be large, where the electronegativity of atoms it ranges from 0.7 for cesium or francium, from 0.7 to 4.0 for fluorine, right, the superhalogen. So, the range is so much, the large values it refers to the tendency to acquire electrons. Electron will transfer from here to here, okay. And this gives them NaCl structure, right. In the NaCl structure, you see them Na ions and Cl ions alternately placed. So, Na, Cl, Na, Cl and so on. So, Na, Cl, Na, Cl, okay, right. This is the Na ion here, right, Na ion here. The bigger ion will be chlorine. Chlorine will be bigger ion because it has got 18 electrons as against 10 electrons which will be possessed by sodium, because it has given already 1 electron. From 11 it has become 10, and chlorine has acquired from 17, the number of electrons gone to 18. So, chlorine is an acceptor, sodium is a gives the electron. Okay. This is ionic solid, this is arrangement of the negative and positive ions in a NaCl ionically bonded solid. This gives the two-dimensional picture of an ionic lattice. As I told you, in a solid there cannot be only attraction. If there is only attraction, the solid will collapse, all the atoms will come close to each other, right. The positive ion, the negative will be attracting the negative ion, this positive also will be attracting the negative, will be attracted, and so this negative and so on. If there is only attraction, what will happen is the positive ion, all the negative ions which are the nearest neighbors will come closer to these ions and they will stick to each other. Then what will happen? The orderly arrangement of ions, as I showed you here, the kind of crystal structure will not be present, right. In order to, there will be no lattice at all, the periodic arrangement will not be there, because the atoms will come and you will have a cluster, right. That is not the real case. In reality, the atoms are arranged according to a different order. There is a interatomic distance or interplanar separation. These things can be measured by X-ray diffraction, as you know. Therefore, you have a regularly arranged lattice, right, ions here. Let me now try to see how the lattice energy can be calculated. What do you mean by lattice energy? I told you about cohesive energy or binding energy. So, the lattice energy is the same, right, the energy required to break the ionic bond. So, what is ionic bonding? It is the bonding between the positive ion and the negative ion, the positive negative and positive negative. If this kind of thing is there, it is an ionic solid. The bonding that exists is the ionic bonding. As I told you, there cannot be only the Coulombic attraction alone. If the Coulombic attraction alone were present, then the lattice will collapse. There will be no ordered arrangement of atoms. As I show here, experiments clearly show a stable solid should have a definite arrangement of atoms, right. So, if you have the atomic arrangement like this, ionic arrangement like this, right, this is again shown here. In order to calculate the lattice energy, right, the bonding energy, what should I do? I should take some ion as the reference ion. Let me take this negative ion as the reference ion, right. This is the reference ion. The negative ion next ion will be positive. Obviously, negative, and negative means there will be ultimate there will be repulsion, right. For stability, every negative ion will be surrounded by positive ion, then every positive ion will be surrounded by negative ion, and so alternately positive ion, negative ion, positive ion, negative ion. Similarly, positive ion here, negative ion, positive, negative. Positive and negative should be alternately placed. That is what you see here. You see here a negative ion, positive ion, a negative ion, and so on, right. So, if you take the negative ion, the nearest neighbors will be positive ions, right, at the same distance or, right. You see the first circle, they are the nearest neighbors. The number of nearest neighbors is called the coordination number. For any given structure, you take a reference ion, the number of nearest neighbors is called the coordination number. So, by looking at the coordination number and other factors, not only the Coulombic attraction should be taken into account, the repulsion also should be taken into account to calculate the lattice energy, right. So, the lattice energy can be calculated. Let me summarize today's lecture. Octet rule plays an important role in all bondings, right. That is number point 1. In primary bondings, electrons adjust themselves in such a way that they attain the octet structure. In all bondings, there will be both attractive and repulsive forces. I told you that repulsive force comes from quantum mechanics, whereas attractive force comes from the Coulomb's law. Let me pass on to the question session. The first question is, what is meant by octet rule? Question number 2, in ionic bonding, how electrons adjust themselves to attain the octet structure? What is meant by repulsive exponent in ionic solids? With this, we come to the end of the lecture 2. We will resume the lectures 3, etc., in the time to come. Thank you.